All right, so let's actually get into some new stuff now. So we're going to be talking now about isomerism. So what is an isomer? Isomers are different compounds with the same molecular formula. So what that means is we're looking at something, we're looking at a molecular formula, and it's possible to draw several different compounds from that. Meaning, when I say different, it means how the atoms are arranged in connectivity, or spatially may be different when you're looking at these different compounds, even though they have the same molecular formula. So there's a lot of different examples of isomers, and we're going to go through some of them in this video. So first, let's talk about constitutional isomers. So these are molecules that have the same molecular formula, but they differ in their connectivity. The more atoms we have, the more constitutional isomers that are possible. So, so talking about it too much, let's just go right into an example here of this organic molecule with 4 carbons. And I've drawn out molecules several different times, and I think for the most part, for all those molecules, there are different ways to draw them. So yeah, let's go ahead and draw this molecule, and I'm going to do it in Lewis structure fashion, just to keep things kind of simple for now. Oops. Just like this. Of course, I would encourage you to try drawing these out yourself before I do it, just to get some practice. Right, so here we go. And of course, this is not 3D spatially correct, but for simplicity, I'm going to keep it like this for now. And of course, carbon can make 4 bonds because it has 4 valence electrons, so remember that. As we can see here, there are 3, 2, 2, 3, so that's 10 hydrogens. There are 4 carbons, so this is correct. Now, there's another way to draw this. I'd recommend pausing the video and seeing if you can draw it yourself, but I will spoil it now for you and do this. And still, each carbon here still has its 4 covalent bonds. There you go. So we just kind of switched, quote unquote, we switched the position of one of these carbons towards the middle, and we see that we have a different structured compound. So these are constitutional isomers, right? There's still 10 hydrogens here, there's still 4 carbons, but they just differ in their connectivity. And as you can kind of see here, and hopefully this is sort of obvious, there's the maximum number of hydrogens on every carbon. And of course, the ones at the end have more hydrogens because they are not having to connect to more than one of its carbon neighbor. But here, because the central carbon is attached to 3 other carbons, there's only 1 hydrogen attached to it. Right? So these are the 2 constitutional isomers that are possible from this molecular formula. And of course, if I give you this formula and you draw out a molecule, you might say, okay, is one of these correct? And the answer is no. Without additional evidence, we don't know for sure what the correct structure is. So if you were making something in lab, for example, and you're able to figure out this is the molecular formula, but you didn't know structurally which one it was, it would be tough to say without any additional evidence. So if we had something like, what's its boiling point, for example, we could know, because these compounds do have different boiling points, because they're connected differently. And we'll talk about that a little bit more in a later chapter, but just something to keep in mind. So another type of isomer is something called a stereoisomer. So stereoisomers are isomers that differ only in how their atoms are oriented in space. Their atoms are bonded in the same order, unlike with constitutional isomers, but they differ in their quote-unquote spatial arrangement. And so stereoisomers are pretty important, and we'll talk about that again in a later chapter. But an example of a stereoisomer is something called a cis-trans isomer, or a geometric isomer. This is one type of stereoisomer where the compounds differ in the geometry of the groups on a double bond. So cis isomers have groups on the same side of the double bond, while trans isomers have similar groups on the opposite side of the double bond. And to have cis-trans isomerism, the groups at the end of the double bond must be different. So let's go ahead and draw an example of that. You notice here with this molecular formula, there are 2 less hydrogens than the previous example. And that'll be important to note here and for a later slide. So here's this compound. Right, there's 2 less hydrogens, so we have to sort of think about what that means. And in this case, with 2 less hydrogens, there is an additional bond somewhere in the structure that takes the place, right, of those 2 hydrogens. Or, right, and see here we have these carbon groups on the same side of the double bond. So this is what we'd call a cis isomer. And so if we were to draw the double bond again, we'll have this carbon group here. It's also called a methyl group. And we will switch this other position. So now the carbon groups and also the hydrogens are on opposite sides. So this is the trans isomer. Right? And this is the cis isomer. Right? So the atom connectivity is the same, right? So you still have this carbon attached to this carbon attached to this hydrogen, this carbon attached to this hydrogen, this carbon attached to that carbon. So they're all the same, right? And we could even, it might not be a bad idea if you want to number these things, right? So numbering the carbons, 1, 2, 3, 4, and it's still 1 is attached to 2, 2 is attached to 3, 3 is attached to 4. We could do the same with the hydrogens, right? 1 is attached to 2, and 2 is attached to 3. 1 is attached to 2, 2 is attached to 3, right? Or, oops, 2 is attached to 3, right? So, as you can see, spatially, or connectively, they are attached to the same molecule, but they're just different in where their arrangement is. And again, without additional evidence of how this is happening, or, how they're connected spatially, either one of these compounds could be technically correct, right? There's no right answer for which molecule is the right drawing, or the right structural representation. So, as you can probably imagine, with that formula that I gave you, and this is the same one here, there's more things you can draw from that, right? There are more structures you can draw that are both stereoisomers and may also be constitutional isomers. But to kind of give you an example of the different ways that these things can come together, let's talk about this first. If you can rotate the molecule around and have it superimpose onto a different molecule of itself, they are not stereoisomers but the same molecule. So what do I mean by that? Let's draw it out. And I'm kind of shorthanding the hydrogen placement here, so I'm kind of condensing it rather than drawing everything out. It's kind of a lengthy process. So we have, the similar one here, this cis isomer. Now let's compare it to this. Right? How do these 2 molecules compare to each other? Are they the same? Are they constitutional isomers? Are they cis-trans isomers? And the answer is they are the same. Right, so these are the same molecule. If we flip it, so one molecule, it can be superimposed on the other. And I kind of have a tool that I can do that with here, to sort of show you proof, right? So we can take this molecule and, here we go, I should be able to, maybe not, maybe I can't do that. Oh, no, I can, cool. The atoms are a little bit backwards, whatever. But we can see here, right? So this is the same molecule, right? So you'll have your CH3 groups up top, right? And you'll have your hydrogens on the bottom. So we can, in fact, superimpose this on top of itself, and it is exactly the same molecule, right? I hope that makes sense. And that'll be, once again, a little important in a later chapter when we talk about different kinds of stereoisomers. To give you sort of another example, let's take, let me see, let's look at this again. right? So if we take this molecule and compare it to this molecule, right? What's the difference here? Are they the same? Are they constitutional isomers? Are they cis-trans isomers? Or are they different molecules entirely? Right. So that'll be kind of something that we'll talk about more. It'll give you plenty of examples of when we start looking at more molecular formulas and figuring out how the structures relate to one another. So I hope that makes sense. Yeah, and taking structural drawings for face value can be tricky. So we'll learn some tricks a little later on when we start being able to name molecules. It'll be a little more readily apparent if they're, what their relationship is to each other. So, drawing molecules in organic chemistry. So, I've been doing a lot of Lewis structures, right? And I've shown you some 3D representation of molecules. But there is a couple of ways we can draw out these molecules, and one that we'll be doing primarily for the majority of this semester and the next. So the first thing I want to talk about is condensed structural formulas. And these slides will be a little bit text heavy just so I have some of the general rules written out for you all to kind of follow. But in condensed structural formulas, all individual bonds are shown, each central atom is shown together with the atoms bonded to it, and the atoms bonded to a central atom are often listed after the central atom. Such as like this, rather than having the actual bond shown, the atoms are just sort of placed next to each other, even if that is not their actual bonding order, right? Because the hydrogens here aren't connected to the carbon, right? They're only one, hydrogens can only make one bond. So these three hydrogens must be bonded to the carbon, right? And condensed structures are assumed to follow the octet rule. So let's go through an example, right? So with this very familiar formula here, drawing out the Lewis structure for this. So Lewis structure. Right, very familiar. Not doing the 3D spatial arrangement for simplicity's sake. Right, here we go. And if we're going to do this condensed, what would that look like, right? So let's kind of break down the components of the Lewis structure first, right? So with this, right, this N group, we would say this is CH3, right? 3 hydrogens, 1 carbon. These middle two here are the same, right? They're each carbon's bonded to, identical components to their left and right. So we would actually say this is CH2, 2, right? There are 2 CH2s here. This last one, still CH3. So in the condensed formula, how we would actually draw this would be like this. And we wouldn't show any bonds, we would just show the just general connectivity. And this is sort of a shorthand, right? This is not typically the way we draw molecules very often in organic chemistry, but this is just like quick, shorthand you might see now and again, especially in your book. It's good to be familiar with this type, but it's not typically how we will be drawing molecules. But it's good to keep in mind, and we'll be doing some more examples of this later on. So, line angle formulas. This is the most common representation for organic molecules. And generally, how line angle formulas work is that bonds are represented by lines, and carbon atoms are assumed to be present wherever two lines meet, a line begins or a line ends. All other atoms, aside from hydrogen, are drawn in line angle structures. Hydrogens are not drawn attached to carbons and are assumed to be there, but are drawn to non-carbon atoms. The angles are shown to best represent the geometry of the carbon atoms, and line angle structures are, of course, assumed to follow the octet rule. Right. So again, this is the same exact formula as the previous example. And this can be a little tricky at first, so this will take some time getting used to. So we'll be sure to be going through plenty of examples where I'll be drawing out these line angle formulas. So hopefully you'll get pretty familiar right away. So what is the line angle formula for this structure? just like that. That's it. It was very, very simple, right? So wherever there is a line, that's where the bonds are. And whenever a line ends or begins, or where lines meet, there are assumed to be carbons with the correct number of hydrogens attached to it. So let's kind of go through this a little bit so you can see what I mean. Right, so this ends point here, right? There's a carbon here. And it's bonded to something. So what is attached to that carbon? Right, as one bond, so what are the other three things attached to it? So they have to be hydrogens, right? And this middle line here, what's attached there? Right, it's a carbon, right? Because it's not shown, so it has to be a carbon. And it is bonded to something else. So that means, right, because carbon has a valency of 4, there's 2 other things attached to it. And those are the hydrogens, right? And so on. So with this other angle here, has to be a carbon, it's bonded to something else, it's missing 2 more bonds, so the hydrogens are here. At the end of the line, there is another carbon. It's attached to 1 other carbon, so there's 3 things left it needs to be attached to. And those are the other hydrogens, right? And what's also neat about this is that the angle between each carbon is 109.5 degrees, right? So the incorrect way to kind of draw this structure is like this, right? You wouldn't draw it like this, because the angles here are 90 degrees, right? So you want these to be a bit more open. You know, and these drawings don't have to be perfectly angled, right? You don't need to get out a protractor or anything. But as long as they're not like sharp right angles like this, then you have the correct line angle structure here, right? And sometimes when we draw out these line structures, you know, you might draw in the carbons just for clarity for a certain problem we're doing. But in general, you will see a lot of formulas being represented like this, right? Just with the line angle formula. And again, we'll be doing plenty of examples of this. So hopefully it'll become a little bit more clear as we get some practice with it. So next, and kind of related to drawing out molecules from like the formulas, we're going to be talking about degree of unsaturation, or DU. So this is a way, and I've kind of been, of course, drawing out the molecule, but if it isn't obvious if there are any pi bonds or rings in structure, how do we know, right? So the way to determine that is just based on this molecular formula. And another example of some of the few math equations, quote unquote, that we'll have in the semester, we have another one here. So the way to figure out degree of unsaturation is by taking the maximum possible number of hydrogens in an organic molecule and subtracting it by the actual hydrogens that exist in the molecular formula and dividing it by 2. And so each degree of unsaturation means that there is 1 pi bond or 1 ring in the molecule. So let's take a look at this example here. So to figure out the number of maximum possible hydrogens, we have to use this little equation, 2n plus 2, right? So for a molecular formula of carbons and hydrogens, n is related to carbons and x is related to hydrogens, right? Looking down at this more simplified degree of unsaturation formula here. So looking at this example, n is 5, x is 10, right? So the du is 2, and n is equal to 5, plus 2, subtracted by 10 over 2, right? So 2 times 5 is 10, plus 2 is 12, minus 10 is 2, so 2 over 2 is 1, right? So there's 1 degree of unsaturation. So that means there's either 1 pi bond or 1 closed cycle in the molecule, or 1 ring in the molecule. So if we were to draw this out, right, so 5 carbons, 10 hydrogens, if I was to draw it out like this, right, with the line angle formula, so if we draw it out like this with the line angle formula, right, we have our 1, 2, 3, 4, 5 carbons, but the number of hydrogens on it is 2 more than that, right? So we have 3 here, 2 here, 2 here, 2 here, 3 here, so that's 12, right? That's the maximum number of hydrogens, so that's not correct. And we know from the degree of unsaturation formula that there is 1 pi bond or 1 cycle. So the way we can draw that out is like this. Boom. So just like that. So there's a double bond in the middle of this molecule, or at the end of this molecule, or somewhere in it. Or it could be a closed cycle, like this. Right? And you can kind of go through and count the number of hydrogens attached to each carbon and figure out where you can figure out the maximum number of hydrogens in each molecule, right? So we know that there are, look at this one, there's 3 hydrogens here, 2 here, and because we have a double bond here, right, this carbon and this carbon, there's only 1 hydrogen here, right, because it's attached to 2 things, but this is a double bond, so that's occupying 2 of its valence electrons, so there's only room for 1 more thing attached to it, right? Same goes for here. And at the end here, we also have 3 hydrogens. So adding them all up, 3 plus 2 is 5, plus 1, 6, plus 1, 7, plus 3, 10, right? And same here, each carbon here is identical, and so we have 2 hydrogens all across the board. So 2 times 5 is 10, right? And what is the relationship of these 2 molecules? They are constitutional isomers, right? They have the same molecular formula, but they are structured differently. So I hope that makes sense. And we could draw out some more examples of these, right? There are more double bond placements we could do to probably make some cis-trans isomers possibly, but I will leave it here for now. So, of course, there's some additional rules to degree of unsaturation, and that is involving when there are non-hydrocarbons present in the formula. So when we have any halogens, since they're monovalent, they count as hydrogens present in the molecule. So you would essentially just say, if there are, for example, 7 hydrogens, and there's a halogen in there, you would say there's actually 8 hydrogens. Oxygen is divalent, so we just ignore it. So if there's an oxygen, just pretend it doesn't exist in the molecular formula. And if there's nitrogen present, because it's trivalent, you have to add 1 additional hydrogen for every nitrogen to your maximum possible number of hydrogens. So let's just go right into an example of that. So we have this molecular formula here, right? So remembering our degree of unsaturation rules with 2n plus 2, we know that n here is 10, x is 15, and so for the degree of unsaturation, it is 2 times 10 plus 2. And now with all this, because there is a nitrogen present, right, we have to add 1. And then we do the final subtraction, 15. Let's add another parentheses here, just for formula's sake. And this is all divided by 2, right? So 2 times 10 is 20, plus 2, 22, plus 1, 23, subtracted by 15 is 8. So 8 over 2 is 4. And we should always have an even number at the end of this. So if you have something like 3.5 or 5.5, I made a mistake when I first did this, and it was 3.5, and I was like, oh, that doesn't make any sense. I had to recheck my math. So you have to always have an even number at the end of this, right? If you don't, you have to recheck your equation. And because we have 4, right, so the degree of unsaturation is 4, so we have, we could have any number of pi bonds or rings, right? We could have, 4 rings, we could have 4 pi bonds, we could have 1 pi bond, we could have 3 rings. And so there's a lot of different examples of what that could mean for the formula. And I won't be drawing out these molecules here. I would encourage you to do it on your own, just for some practice. But if you draw it out and you're like, I have the 4 degrees of unsaturation here, but I don't know if this is correct, just go through and count the number of carbons, hydrogens, and in this case nitrogens, and see if it comes out to the example total here. And as long as you're following your octet rule, right, make sure everything is happy and there's no formal charges, you should be good to go. Maybe we'll go over these examples in class and draw out some different molecules and see, if there are any isomeric relations between them. So in this example here, right, we have N is 7, and for the case of hydrogens, right, it's not 9, but it is 10, right, because we have a halogen here, bromine, and we count that as a halogen. So the degree of unsaturation for that is 2 times 7 plus 2 minus 10, and that equals 3. So it has 3 degrees of unsaturation, so there could be, again, any number of pi bonds or rings in this system. And with this, too, like with pi bonds, you could have, so a double bond would count as 1 degree of unsaturation. A triple bond, of course, would count as 2, right, because there are 2 pi bonds connecting those 2 carbons together. Right. So if that makes sense, and again, I would really encourage you to just try to draw out some of these different examples on your own, see if you can find some structures that make sense.